All right, so the last thing I want to do, or actually not the last thing, but we're going to talk about one more base, and then we'll go through some properties. Okay, so remember, as soon as you see that there is not a number written, you need to assume that your base is 10. Because it is 10. If it's not written, it's 10. Now, there's one other type of base that follows that same rule, and that's a base of E. And E is a number 2.718384. It goes on and on and on forever and ever and ever. Never stops, never falls into a pattern of repetition. So we call it irrational. Okay, now another number that you know of that's irrational is pi. Okay, so pi deals with circles. So it's the area of a circle, circumference of a circle, volume of a sphere, whatever. If it's circular, it deals with pi. If it's money, it comes from E. Okay, E's job is to play with money. Pi's job is to play with circles. So E's job is to play with money. So that is, it's not just some number that somebody made up one day. It has to do with interest, and we'll actually deal with it later in a different section. For right now, you just need to know it's a number. It is not a variable. Okay, its value does not vary. It is a symbol for a long number that I could never stop writing. Okay, because it never stops. So just like pi is a number, E is a number. Now that being said, if you have log base E, so remember there's an infinite number of bases. They're all positive. If it's not written, it's a base 10. Well, if I say log base E of whatever my argument is equals my exponent. Okay, that was too many E's. All right, so log base E of an argument equals my exponent. All of a sudden, we've got all these letters. So it's going to be easier for us to say the natural log. So log base E, instead of writing it that way, we're just going to say the natural log, which is ln. It's backwards, I know. You think it should be NL, but we get it from another language. And so the first letters of each word are reversed. So it's like logarithmic natural or whatever. Anyway, so it's ln. It's not, that's not how you read it. The way you read it is the natural log. Okay? Just remember, it's still a log. It's just that its base is E, which is a number. Okay, so as soon as you see like ln3, that means the logarithm base E of 3. We call it a natural log because not only does E deal with money, but the more that we play with it, we find out that, and again, you'll find this later, but just to give you a little hint, it's called the natural log because like population growth, if it follows a natural pattern, we'll deal with E. Okay, population decay, if it's done naturally, will follow E. So if a population is growing or if a population is decaying. So cancer, okay, the way that cancer will multiply, the cells will multiply, can be ascribed to E. Okay, so it has a lot of stuff, and since it's all done naturally, we call it the natural log. Okay, now we have to do properties of logs. So first of all, let's do some graphs. Okay, so just like with exponentials, if your base is improper, then your logarithm will increase. Now, it's going to look different. Okay, if your base is improper, your logarithm will increase. So if it was exponential, it would look like this. If it's a logarithm, it's going to look like this, and it's going to go like that. Okay, so it's still increasing. As you read it from left to right, the graph still goes up. However, it's just a different type of increasing. This one increases really fast, and this one just increases very slowly over time. If your base is proper, or if your base is elementary, it's going to decrease. Okay, so decreasing this way with an exponential would have looked like that. Decreasing with an exponential would have looked like that. decreasing on a logarithm is going to look like, will look like this. Decreasing. Okay, so this is increasing. So a decreasing logarithm will look like this. Okay. So you'll notice that these two kind of sort of mirror each other this way, and these two will kind of sort of mirror each other this way. So those are your graphs. So that's how you can figure out what your graph is starting to look like. So just like an exponential, if an exponential, every exponential function travels to the point 0, 1, well, every logarithmic function, unless I move it, stretch it, do something, will travel through the point 1, 0. So how do you keep it straight? I taught you exponentials first, and 0 comes before 1. Or this looks like an L and an O. Okay, this looks like an L and an O. So every logarithm will travel through 1, 0, which looks like an L and an O of log. Okay. Another thing, remember with exponentials, every exponential, unless I moved it, stretched it, whatever, would travel through the point 1, base. Well, a logarithm will travel through the thing base, 1. So if you'll notice, they flip-flop each other. Okay, they flip-flop each other. They are actually called inverses of one another. They are inverses of one another. So exponentials undo logarithms, logarithms undo exponentials. Just like addition undoes subtraction, just like division undoes multiplication, those are inverses. Well, exponentials and logarithms are inverses of each other. So now we have basic stuff about the graphs. Now we want to look at some properties of logs. And they seem to come out of left field. Okay, they're like, are you just making stuff up or what? Well, remember that the answer to a logarithm would have been an exponent. So we're going to use exponent rules to explain our logarithms. So first of all, if your argument is 1, so I'm just going to use log base A because I don't care what your base is. All of these rules apply. Okay, I don't care what your base is, so all these rules apply. If your argument is 1, then this whole thing equals 0. If your argument is 1, this whole thing will equal 0. Why? Because any number raised to the 0 power equals 1. So all I did was change it back into exponential. Any number raised to the 0 power equals 1. If your base and your argument match, so I have log base A of A. If your base and your argument match, they're the same number, then it will immediately equal 1. Now, why is that? Any number to the first power is itself. Any number to the first power is itself. Okay, so those are your two big things. Okay, if you see a 1 right here, it just goes to 0. If your base and your argument match, you can simplify this thing down to be 1. So another thing is, if I've got a log and I don't care what the base is, but I've got multiplication on the inside. So I've got an x times a y. I don't care what x is. I don't care what y is. I do care that it's multiplication. I can separate that out to 2 separate logs. So each factor will get its own log. Hang on, I'm looking for a blue pen. Are you blue? Ooh, you are blue. All right, so each factor gets its own log. So I'm going to say log base A, log base A. Well, this factor is x. This factor is y. If it's multiplication on the inside, it will be addition on the outside. So I can separate it into 2 separate logs. You're like, are you serious? What is going on? Just remember, if your bases match, so if I have x squared times x to the 4th, if your bases match and it's multiplication, what do you do to your exponents? You add them. Okay, so my bases match. I'm working with a multiplication problem, but remember the answer to a logarithm would have been an exponent. So I just add them together. Okay, so there is a reason that you're doing what you're doing. So I can use the same type of thing. So let's do log A of x times x. Okay, so it's the same number. Well, if it's multiplication on the inside, I can break it out with addition on the outside. So I'm going to have log A of x plus log A of x. That's supposed to be here. Sorry. Okay, well now I've got two of the exact same thing, so I can combine like terms. So I have 2 of those. Now, a little shortcut is this. If you have an exponent attached to your argument, so this would have been x squared. If you have an exponent attached to your argument, you can drop it out front as a coefficient. So instead of writing a 2 on your argument, you can write a 2 out front as a coefficient. Okay, so another one is going to be division, and it goes along the same lines. So if I've got log base A of x over y, okay, so I'm going to show you why it works first. I can bring that up, and I can say log xy of -1. Remember, this has an exponent of 1. Okay, I can bring it up top by changing the sign on my exponent. So if it's y to the +1 in my denominator, it'll be y to the -1 in my numerator. Well, now this is a multiplication on the inside. So change it to addition on the outside. So log A of x plus log A of y to the -1. Well, what did I just learn I can do to exponents? I can drop them out front and change it into multiplication, or change it into a coefficient. So that -1 drops out front, and now it's plus a minus, or plus a negative, which means this is now log A of x minus log A of y. So if it's division on the inside, it will be subtraction on the outside. Okay, so what we call this is expanding. I have taken a single log and I have expanded it into multiple logs. Okay, now I can work backwards. If I have multiple logs joined by subtraction, if it's subtraction on the outside, what is it on the inside? It's division. You just got to remember whoever has the leading negative will be in the denominator. Okay, so since this is leading off negative, he'll be in your denominator up here. Okay, so those are your basic properties of logarithms. So what we are going to do in the practice is we're going to work through them and do examples. That's what we're going to do.